A complete overview of the entire process of thermal power generation. This is a thermal power plant. To generate electricity, workers take the coal delivered by train and, using a coal conveyor belt, transport it to the power plant's coal feeder. The coal passes through the coal feeder and flows into the pulverizer below. The pulverizer grinds the incoming coal into a powder. These fine, pulverized particles are then carried through an air duct to the burner. Here, the coal powder is ignited. The resulting high-temperature heat is used to boil water. The water initially enters through these pipes. The water travels up along the pipes and then reaches the boiler's economizer. The economizer can improve the boiler's thermal efficiency and save fuel. Next, the boiler water moves to this steam drum. The steam drum separates water from steam. After passing through the steam drum, the water flows to the area around the boiler. These densely packed pipes are known as the water wall. The boiler water flows down along the water wall. During this process, the boiler water absorbs the heat generated by the burning coal powder, thereby producing high-temperature, high-pressure steam. This steam then passes through pipes and returns to the steam drum. These pipes at the top of the steam drum are the steam pipes. The steam is represented in red. This separated, high-temperature, high-pressure steam is then sent into the superheater for further heating. Here, the steam will gradually transition from a saturated state to a superheated state. However, the steam's temperature is still not high enough. Therefore, the steam is then sent into a second superheater for continued heating. On the superheater, there are several pipes that lead to the outside. Once the specified temperature is reached, the superheated steam will travel along these external pipes to the main steam stop valve located here. The stop valve can regulate the flow of steam to the gas turbine. In an emergency, the stop valve can completely block the passage of steam. The steam then proceeds to the secondary valve. These valves are controlled by the power plant's automation system. They are able to respond quickly to changes in pressure and temperature to ensure the safe operation of the equipment. Then the steam passing through the valve will travel through the steam pipe to the gas turbine unit. There are a total of 3 types of gas turbine units, namely the high-pressure gas turbine, the medium-pressure gas turbine, and the low-pressure gas turbine. The high-temperature and high-pressure steam will first pass through the pipe above the high-pressure gas turbine and enter the interior of the gas turbine. At this time, the pressure of the steam has reached 178, and the temperature has reached 540 degrees Celsius. After the steam enters the gas turbine, it will expand rapidly, thereby pushing the gas turbine to rotate at high speed. The speed can reach 3,000 revolutions per minute. Let's take a closer look at how the gas turbine works. This is a small pinwheel. When we use the steam generated from boiling water to blow on the small pinwheel can rotate quickly. If we replace the small pinwheel with a gas turbine blade, the blade can also rotate in the same way. But there is a problem. A single set of blades will cause a large amount of steam to be lost. To solve this problem, we can add another stator blade and a rotor blade. Among them, the stator blade does not rotate. It is only used to change the direction of the steam. When a large amount of steam comes in from the side, it hits the stator blade. The steam changes direction and then comes to the rotor blade, generating an upward thrust, driving the rotor blade behind it to rotate along. To ensure that the steam can be fully utilized, we can add more rotors and blades, which generates more kinetic energy. If you look closely, you'll see that the blades of the steam turbine are a lot like an airplane's wings. The top is a bit longer than the bottom, so the steam has a longer distance to travel along the top. To cover a greater distance in the same amount of time, the steam on top must flow faster. The faster the flow, the lower the pressure. This causes the pressure below to be greater than the pressure above, creating an upward lift, which pushes the blade and makes it rotate. This is actually the fundamental principle of a steam turbine. But there's a problem. After hitting the blades, the steam loses energy, causing the pressure to drop to only 858 and the temperature to fall to just 340 degrees Celsius. Therefore, to improve the steam's efficiency again, the steam that has already done its work will then flow out through the steam pipe at the bottom of the high-pressure turbine. This steam will be sent to the reheater inside the boiler to be heated again. Just like the superheaters, there are multiple reheaters, and they are located at the top of the boiler. After being heated by the main reheater, the steam immediately goes to the secondary reheater for further heating Once it's heated to the specified temperature and pressure, the steam will flow out of the boiler through this yellow pipe. Then, following the pipe, the steam first reaches the turbine's reheat valve. Like the main stop valve, the reheat valve can also control the flow of steam entering the steam turbine. It has a valve inside. When the demand for power generation is low, the valve will partially close in order to limit the steam's flow and pressure. When the demand for power generation is high, the valve will open completely, thereby ensuring the maximum flow of steam. After being precisely controlled, the steam then enters the next turbine, which is the intermediate pressure turbine. Same as the high-pressure turbine, propelled by the high-temperature, high-pressure steam, the intermediate pressure turbine will begin to spin at high speed. After that, the steam that has done its work will then arrive at the low-pressure turbine. The steam that reaches the low-pressure turbine, although it has already lost most of its pressure and energy, is still powerful enough to drive the low-pressure turbine into rotation. As the steam passes through the high-pressure, intermediate pressure, and low-pressure turbines, it converts thermal energy into mechanical energy, which in turn drives the generator behind it to produce electricity. Next, let's take a detailed look at how a generator produces electricity. Let's first look at an experiment. This is a coil. The coil is connected to a galvanometer by wires. When a bar magnet is used to move back and forth inside the coil, the galvanometer's needle also moves back and forth accordingly. This is because the coil cuts the magnet's magnetic field lines, thereby generating an induced current. This phenomenon is known as electromagnetic induction. The underlying principle of a generator is actually electromagnetic induction. A generator is mainly composed of two parts, a stator and a rotor. But what's different is that the generator's rotor does not use the permanent magnets mentioned earlier. You can imagine, for such a large permanent magnet, trying to install it accurately into the rotor's slots would be extremely complicated. Even if it could be installed, as time goes on, the permanent magnet's magnetism would gradually decrease. So, how can we solve these problems? Let's look at another experiment. This is a coil. When an electric current is passed through both ends, it generates a magnetic field around the coil. This coil is an electromagnet. This type of electromagnet isn't much different from a common bar magnet. The only difference is the electromagnet's magnetic field disappears when the power is cut. If you increase the voltage, the magnetic field will continuously get stronger. In fact, generators use electromagnets. It is composed of 4 sets of coils. Since the electromagnet is not powered on at first, it is very convenient to install. All you need to do is take the 4 sets of coils and wind them separately onto the 4 protruding magnetic poles, and that's it. This combination of coils is also known as the excitation winding. For the winding to generate a magnetic field, it needs to be supplied with electricity. Therefore, there is also a DC power source here. The DC power source, through 2 wires, connects to the 2 slip rings of the rotor. This way, the winding can generate a very stable electromagnetic field. To make the explanation easier, we will now take one set of the stator coils. To look at it individually, when the rotor's magnetic field lines cut through the stator winding, according to the law of electromagnetic induction, the stator winding will generate an induced electromotive force. When the rotor's end pole is in this position, you can see that only a few magnetic field lines are cutting through the stator winding, but as the rotor turns, more and more magnetic field lines cut through the stator winding. The resulting waveform is as shown in the figure. As the rotor continues to turn, the number of magnetic field lines cutting the stator winding decreases again. The resulting waveform also begins to drop. After a quarter turn, the S-pole arrives at this position. But compared to before, the magnetic field lines are in the opposite direction. So, as the rotor continues to turn, creating waveforms in opposite directions, which is what we commonly call alternating current. We'll add the other 2 sets of stator windings back in, and the phase angles of the 3 stator windings are 120 degrees apart. This way, when the rotor spins, what we get is a 3-phase alternating current. The stator windings of a synchronous generator use a star connection. The starting ends of the 3 windings are connected to the live wires of the 3-phase AC. The other 3 ending ends of the windings are connected to each other, forming a neutral line that connects to the neutral wire. Then, these components are placed inside the stator frame, and a generator is assembled. When a steam turbine is used to drive the generator's rotor at high speed, the generator can then produce electricity. However, there's a problem with this type of generator. there is a large gap between the two magnetic poles, known as an air gap. If the rotor spins at high speed, the air gap will increase the generator's magnetic reluctance, reducing its generation efficiency. Therefore, thermal power plants generally use this type of generator. Its principle is the same as the generator mentioned earlier, except its rotor is cylindrical. It doesn't have protruding magnetic poles, is also longer, and has no air gap, so the rotor can spin at a much higher speed. Additionally, a longer rotor will also generate a stronger magnetic field, so the generator will produce more electrical energy. This electrical energy is then sent to a transformer to have its voltage stepped up. After the voltage is stepped up, it can be transmitted across the country. Now that we understand the principle of how a generator works, let's go back to the low-pressure steam turbine. The steam that has finished its work in the low-pressure turbine is not actually wasted. This steam will leave the turbine and then enter the low-pressure section, the condenser at the bottom of the steam turbine. Inside the condenser, cooling water is constantly circulating. As a result, when the steam gets cold, it condenses into water. Then, through a collector at the bottom, the condensed water is collected. As the condenser cools the steam, the water in the condenser pipes absorbs heat. This causes the temperature of the cooling water to become very high. To cool it down, the cooling water is sent to a cooling tower. Now, let's take a look at how the cooling tower cools this water. First, the hot cooling water travels along hot water pipes into the cooling tower. Cooling towers are made of concrete and can typically reach heights of up to 200 meters. The inside of a cooling tower is not very complex. It mainly consists of a basin, air inlets, heat dissipation packing, a sprinkler system, and a water reservoir. The hot water passes through an inlet and first arrives at the sprinkler system. After that, the hot water reaches the heat dissipation packing. The packing material increases the time the cooling water stays to ensure there is enough time for a thorough heat exchange. Then, the air inlets below draw in large amounts of natural air from the outside, which in turn cools down the hot water. After being cooled, the water flows through outlet pipes at the bottom and returns to the condenser for the next cycle. You may have noticed that cooling towers generally have this design that narrows in the middle. This design allows the natural air, after it has cooled the water, to accelerate its upward flow, thus carrying the heat out of the tower quickly. Because water vapor gets cold, it condenses into tiny water droplets. That's why we often see large amounts of white smoke coming out of cooling towers. That is actually not harmful exhaust gas. Because water vapor gets cold, it condenses into tiny water droplets. That's why we often see large amounts of white smoke coming out of cooling towers. That is actually not harmful exhaust gas. That's why we often see large amounts of white smoke coming out of cooling towers. That is actually not harmful exhaust gas. That is actually not harmful exhaust gas, but rather water vapor. Let's go back to the condenser. The condensate water cooled by the condenser then flows out through these pipes. It then travels all the way up to this low-pressure heater. The low-pressure heater can preheat the condensate, thereby increasing thermal efficiency. At the same time, it also prevents the condensate from entering the boiler directly, which could cause damage to the boiler equipment. The heated condensate water then makes its way to the deaerator here. The deaerator also heats the condensate. At the same time, it can heat the water to its saturation temperature, removing oxygen and other gases from the water. This helps prevent equipment corrosion. The treated condensate then passes through the pipes to re-enter the economizer inside the boiler. Then, the next steps are just as we mentioned earlier. The entire system will then begin the next cycle. It's important to note that the boiler's combustion produces a large amount of flue gas. This high-temperature flue gas first passes through the economizer, which preheats the water inside it. As the flue gas heats the water, its own temperature also drops. This improves the boiler's thermal efficiency. This is the fundamental reason why an economizer saves fuel. The flue gas that has passed through the economizer then travels along the pipes to the flue gas treatment equipment. This is the denitrification unit. By spraying a denitrification agent into the reactor, ammonia is caused to react with the high-temperature flue gas. This reduces nitrogen oxide emissions. The treated gas is then sent to an electrostatic precipitator. Since the ash particles carry a positive charge and the electrostatic precipitator's collection plates have a negative charge, based on the principle of opposite charges attracting, the ash particles are attracted to the collection plates. At the same time, the collection plates vibrate at a high frequency. This shakes the ash particles that have attached to the collection plates, off and into the ash hopper below. The flue gas, after dust removal, then arrives at the next unit, which is the desulfurization tower. In here, the flue gas reacts with water and limestone. This reaction removes the sulfur dioxide from the flue gas, thereby reducing air pollution. The flue gas, after being treated in the desulfurization tower, can then pass through this chimney, which is over 100 meters tall, and be released into the atmosphere. And the desulfurization process generates a large amount of gypsum. After this gypsum is processed, it can be used in building materials, agriculture, and industrial sectors.